So we are talking about how the overall ecosystem looks like when it comes to managing composable memory. And this is in the context of how the CXL is progressing as we go from 1.1 to 2.0 to 3.0 and beyond. So most of my discussions will be mostly architecture and sort of workload related. I won't be talking about anything product specific. Thank you. So we will talk about how what people call these days as a data center of the next generation, how that is shaping out to be, how the traditional server-based architectures are giving way to more composable, software addressable sort of architectures, and how CXL will play a role in creating fabrics and sort of ensuring that you have the optimal use of the hardware resources when it comes to deployment at scale. So let's jump straight into it. So basically, what is CXL trying to do? We are trying to make data appear closer, or we are trying to take compute near data and then basically act on it sooner. So those are the two major trends that we see when it comes to the CXL interconnect. And this in turn will lead to a whole new set of accelerators, a whole new set of GPU, FPGA, DPU technologies, which will make use of CXL-based connectivity to access data, get learnings from it, and process it independent of the server CPU. What it also means is, some of the questions that were asked earlier, you don't need to have one type of drivers for managing storage, one type of drivers to manage persistent memory, something for DDR5, something for DDR4. It all has to be homogenized so that you are able to, the application should see this thing as completely transparent, that there should not be a need to change the application because you managed to add in a module for CXL or attach something NVMe over Fabric. It should be completely transparent to that. So that's the goal. And as we march towards it, basically the whole ecosystem has to play a role to bring it all together. So left to right, this is just a progression of how we see it. Direct attached memory to the socket, everybody knows about it. There's only so much you can scale using it. Some of you must have done DDR controllers and layouts, and expanding it to 20 channels is crazy. So what's the next best step? You can do some sort of a scale-out memory. This is where the first generation of CXL comes into play. And this is where hyperscalers and enterprise and HPC workloads have specific bandwidth per core or capacity per core numbers. And as the number of cores increase, these are the ways in which you can manage those requirements. Like if someone says, I need a workload which requires 5 gigabit per second, then if you can't meet that bandwidth, then that application suffers. And hence the scale-out memory using direct attached CXL capable buffers is the first step. Now things get really exciting when you talk about pooling and disaggregation, because in that scenario, what happens is not only you are able to meet the application performance, you are able to meet it most optimally. So the earlier speaker talked about how you can tier DDR5 with DDR4. This is one way of sort of mitigating the costs of DDR5. Or how do you manage to tier, maybe some sort of low latency flash. And what that will do is your BOM cost of the system goes dramatically low. And whatever is the impact to the application, now you have you have a sliding scale. Like maybe I get hit by 5%, but my BOM cost dropped by 30%. Is it acceptable? The other thing we should also note is that many of these applications have always run on 2-socket systems. So the best NUMA hop they have seen is 1 hop away. Maybe they don't need that latency. Maybe it is something that they can tolerate higher latencies. All of these things have to be tried out. All of these things have to be tuned and made acceptable. And again, this is Siamak was saying, it takes a village. The amount of stakeholders who show up in the CXL ecosystem, this is not something which one vendor can do alone. So coming to runtime memory management, so as I mentioned, we had direct attach, scale out, and pooling. And that's how the system memory composability sort of increases. Now, there are various ways of doing it. You can do memory tiering and page migration. We'll talk about that. Multi-type memory management. I think some of the options on multi-type memory have been getting whittled down recently, but you can use SSDs, or you can use NVMe over Fabric to sort of create that. And finally, there have been many public papers where folks have talked about how memory has been left stranded, how memory is not able to be optimally attached to a given server. So how do you borrow that memory? How do you allocate that memory on demand as required, and in general sort of reduce the overall capex costs for a data center? So when I talk about tiered memory, it's we can call it hot, warm, cold, or hot and cold. One way of mitigating the longer latencies is to do some sort of page migration, where you are able to sort of detect if a particular page is looking hotter, and in which case move it to closer memory, closer in latency. If a certain page is not getting many accesses, then you kind of say that let's demote that page to a colder memory tier. So this is one way of describing it. I'm in marketing, so I'm not going to go too much into this. But enough to say that we have these the sort of the static resource allocation tables and the heterogeneous memory attribute tables, which tell you what type of memory it is, what type of bandwidth it is, how much latency it is, and then accordingly allocate the processor accesses to that type of memory. And so when it comes to tiered memory, we talk about page migration, and one of the ways of doing it is either you give the control to the software, or you sort of do it in hardware. There are pros and cons to both approaches. If you do it in software, typically your hypervisor, your application has a far better understanding of when it is seeing a slowdown in performance, in runtime performance. On the other hand, if you do it in hardware, then the performance is better. It may lead to unexpected behavior at times, but both are the approaches which can be used. And we have seen both type of approaches being explored in the ecosystem. So when it comes to like page migration, typically, what do? You track the accesses going to a particular page. You see if there are page misses. You see if there are hits. And in general, sometimes it's the hypervisor. Sometimes it is some kernel level module which determines, does that page get to stay in its hot or cold place, or does it need to move? Whether you do page migration also depends on how long is that application running. I mean, we have heard of microservices and this type of serverless use cases where applications live for seconds. I mean, there might be scenarios where before you can migrate the page, the job is done. So again, it's a process which we have to go application by application and workload by workload to figure out if page migration will indeed be useful, or how does it work to improve the performance. One thing that we always also get asked about is what is the security in this whole process? I mean, when you are talking about, people are used to a core and a DRAM attached to it. And that is part of a trusted enclave. And, if you are hosted on public cloud, the hoster doesn't know what application are you running, and you are guaranteed that privacy. And the same privacy has to extend when you are dealing with CXL attached or a fabric attached memory. I mean, that particular secure environment has to be extended to the DRAM, to the direct attached CXL buffers, or over to fabric. And that shows up as a lot of use cases where a lot deeper dive is required, and a lot of debug is required. So in this particular case, I would say the right-hand side sort of represents the simplest way in which you could allocate a memory pool. It's a multi-headed device, and you have two hosts accessing distinct regions in the memory. Fairly simple, and that should be the first solid step that the whole ecosystem should take to ensure that a memory pool can indeed be created. The middle picture is sort of a more generic view where you have a switch. There are CXL switches around, and you are able to have multiple hosts and multiple targets in terms of endpoints, and all of them can be accessed from any host. And naturally, this leads to other considerations such as loaded latencies and buffering of memory, and how many reads to how many writes, and how the switch handles it. The fun really starts in the first picture, where now you have multiple tiers and multiple hosts, and now when you have so many applications accessing different types of memories, different tiers of memories, what are the read-write patterns, what are the latency requirements, all of these become harder and harder to quantify. And again, this is the place where more application level tuning is required, more sometimes you may have to put bounding boxes on, these are the 4 types of applications that work on that particular system. Many of the enterprise use cases are fairly limited in the type of applications they use. So that's one way to sort of achieve a high performance system with pooled memory as you take the initial steps. There are new functions or new devices or new modules which will be required in hardware and software as we look at runtime memory allocation and pooling. There are some people talk about hot plugging of memory. That's a very a use case which exposes a whole bunch of it shows how well compliant you are with the CXL spec. What also happens at times is that there are certain devices which may be physically attached, but they may change their functions. And in that case, even though the hot plug is not a physical hot plug, it still looks like a logical hot plug. And as a result, you still have to deal with the fact that there was memory which was visible as part of the system, and suddenly it has vanished, and maybe it came back as a memory of a different type. So, this is something which is we had software vendors talk about it. We had memory vendors talk about it. So this is something which has to be all pulled together in terms of some sort of a bake-off or some sort of a demo where everybody benefits from the learnings that have been gained as part of the CXL ecosystem. And then, finally, what I would say is that the goal is to get to composable and disaggregated modes, not because it's cool architecture. It's because it solves problems related to costs, performance, and power. And if there is money to be saved or money to be made, people come together and they solve the problem. And what we want is the many use cases. We just don't want a cloud focus or a HPC focus. I have searched high and low for, say, a telco use case which required memory, or a fintech use case, or something related to healthcare. So we have to look across the spectrum in terms of verticals and applications to figure out what will work for CXL and what won't. And finally, this is true as hardware vendors are extremely aware of. You cannot pay anyone enough money to change software. So you have to work by keeping the application as it is. And many people have tried that option of, I'll give you more performance if you change your application, and it never does really work. So application transparency, it shouldn't matter whether you're running on direct attached memory or some sort of scale-out memory, or you're completely running out of a memory which is attached to a fabric. It should still look the same. And so that's again the goal when we look at runtime composable memory. I think that was my last slide. If we have time for questions, I can take it. All right. Thank you. Oh, there's a question. Sorry.
So is AMD going to look at some more development kit like other vendors are looking at for memory pooling, tiering, optimizations of software stack on the host? Is there any plans for AMD for another development kit?
I really can't talk product specific, but we are an active member of the consortium, and we see where the trends are going. So yeah.
You mentioned on the disaggregation and the composable part of it, you mentioned security. But from a security point of view, what do you think are the problems to be solved? Or at least is the consortium looking at solving the problem? Like, is it access control? Is it ensuring trusted execution environment and things like that? Is the consortium already solved it, or is it all to be solved? Or what about also like link encryption? Maybe I asked the question earlier.
I really don't know.
Okay.
I just know that just the way when you boot your server, and when you say I have so much amount of DRAM and then I have so much amount of CXL memory, there should not be any hesitancy from anybody saying, well, my data is residing in CXL memory, so is it safe? Is it good? I think it should be treated on par as regular, tier 1 local socket attached DRAM. Okay. That's the goal. Again,
so you're saying it's more of a hardware platform service to assure security of the
yes.
components, and then the software will just consume it.
Correct. And sometimes there are cases where people ask whether is PCIe based IDE, will you use link encryption, or will you use your own technology, and these are sort of problems in flight. I don't think we have the final answer on all of these, but in general, from a server platform point of view, most of the ecosystem looks towards the server vendors to figure out how the security is being determined.
Okay. Thank you.